Hey y'all, can you hear me?
Yes.
Okay, sounds good. Interesting. We have only two people here right now.
It's weird seeing you without a mask on, huh?
Yeah. Feels a little bit more comfortable, although I'm pretty used to it. That
I would bet it's nice being at home having one off all day. I couldn't imagine trying to lecture with one on.
I guess you definitely get used to it. I have to admit, I don't seem to mind masks a whole lot. I definitely prefer not having them on, but it wasn't bad. So.
Right, yeah. I used to work in a restaurant with one on, and you can imagine that's probably the worst case scenario for it right there.
Mm-hmm. Yep. I gotcha.
But just everyday like grocery store stuff, it's chill.
Then it's not as bad since you're not having to talk. The other nice thing is I can drink now, and my voice gets scratchy after an hour and a half, well, 3 hours of lecture, because I go and I lecture immediately after this, as no one knows.
Yeah, I just go from one Zoom to the next.
That's also going to be a little easier before to get to the next class, and I was trying to eat some lunch in between, or just a snack. Now it'll be a little simpler. Okay, well, welcome y'all. So first day at home, and like I said, it'll be a few weeks, and then hopefully can go back to being in person again for those of you who want to do in person. I am just going to have my video on for maybe a minute or so, and then I'm going to stop the video because of me, the camera, just because the internet here is on home is not as fast as it is at the university. So I want to make sure I have all the bandwidth going to Zoom. Just a reminder, office hours today from 2:45 to 3:45, tomorrow from 2 to 3. Normally they would be Monday from 2 to 3, but because I had to cancel them unexpectedly yesterday, I'm holding them tomorrow. So today we're talking about entity relationship design terminology. And I sent out an announcement, but I want to make sure everyone knows. I moved everything back by one class period. So if you look at the notes here, you see there's a jump from 2.9 to 2.16. And that's because on the 11th, which was last Thursday, I was lecturing on both the relational algebra, calculus, and entity relationship modeling. It just was starting to, it's not really good to slop over from period to period. So I kind of want to get everything back where I have lectures that don't slop over from period to period, that end at a reasonable time. And I had a available slot at the very end, that very last day of class before I had canceled it. Now it's just we have a last day of class, so there's no it didn't cause anything to be pushed out of the schedule. It also had some good benefits. I pushed the next 3 homework assignments back by 5 days. So the next 5 assignments are due on Wednesday, essentially Tuesday evening. So the next assignment's not due for a week. And then I didn't have to push the last database assignment back because you already had a huge amount of time, a week and a half for that. what I did push back was the exam by a week. And what that allows me to do is test you exclusively on databases and test you on NoSQL and MongoDB, because you can see that the last database homework is due essentially Tuesday evening, and there's no late submissions, need to spell that correctly, accepted for that one, because what I'll be doing is immediately publishing the homework solution so that you have at least a day to study the solutions, and so you're ready for the exam. So I actually have one lecture where I kind of introduce web programming and scripting languages, and then we'll have the exam, and then we'll dive into scripting languages. So I think this works out better, because before you weren't going to see the solutions to the last homework assignment before the midterm. And remember, there's no final in this class, because the web project that you're going to be doing at the end of class is going to be replaces the final. So questions about any of this? I also pushed the quiz deadlines back, so everything should be synchronized now. So any questions about any of this? Okay. So I'm going to, oh, go ahead. I'm going to stop the video of myself at this point, because I don't want to take that load. Okay, I heard someone had a question.
Yeah, as you were just talking, I just realized that one of the lectures has passed me by, the one that's due today at 11:30. And is there, I'm not too familiar, I'm trying to think about the policy for this. What is the policy for either late, or is there like a dropped homework or quiz or something like that?
Yeah, so I drop, I forget whether it's 2 or 3 of the quiz scores. I think I dropped
you do?
2 of the quiz scores. So for exactly this
God.
reason. I don't give extensions,
Okay.
because then it's just too hairy. So the way I do is I just drop a couple of the quiz scores and no questions asked.
Okay, wonderful. Thank you.
You're welcome. Other questions? Okay. In that case, let's get started. And I'm going to do a quick review of I know that I started talking about the entity relationship model last time and how we use it for doing database design. So I'm going to quickly go through the first part of the lecture again, and then I'll slow down when I get to where I left off. So basically, there is 3 essential things. There's the basic concepts with the ER model. There's this diagrammetric language that's called the Unified Modeling Language, and is also known as ER diagrams, and I'll refer to them usually as ER diagrams rather than UML. And then there's a couple so-called connection traps that come up with ER models that we'll talk about at the end of lecture today. Okay, so we talked about last time 3 basic concepts in the entity relationship model. There's entity types, which are essentially your physical entities, things that have an existence somehow in this world. Now, if you have a virtual environment, there could certainly, like a online website, there could certainly be some virtual entities there, but they're things that kind of exist, have an independent existence, like staff or branches or properties or owners. And then we have relationships between entities, like branch employee staff, or we have a guest books a hotel room. So we have relationships, and those are denoted by foreign keys in our relations. And then finally, we have attributes, obviously the same thing that we have with relations. And in general, entity types will get mapped into relations, we'll find that binary relationships get mapped to foreign keys, that multi-degree relationships, anything above 2 degrees, tends to be mapped into its own relation, and that attributes can be associated with either entity or relationships. Okay, so we've gone through that. So with the ER diagram, a rectangle with a labeled rectangle is used to denote an entity. And then if you have a binary relationship, that is denoted with a directed arrow, and it typically is directed toward the entity that has the foreign key. So in this case, staff is the one with the foreign key, and so the arrow is typically directed toward that entity. So that's actually important enough that I shall write it down. So typically, so in a binary relationship, the arrow is typically directed toward the relation or entity. I'll say entity that stores the foreign key. So make sure, first of all, in your homework assignments that binary relationships are directed, and I'm not going to deduct points if you do the arrow the other way, but I'm just telling you it typically makes more sense to direct the arrow toward the entity that stores the foreign key. And the reason is I want your relationship names. I said this last time, so I'm not going to repeat on a slide, but I want your relationship names to be active verbs if possible. And it's a lot easier for it to be an action verb if it points toward the entity that has the foreign key. Whereas if you go the opposite way, it tends to turn it into a passive verb. So if I directed it from staff to branch, then it would be something like staff belongs to branch or is employed by. Is a passive verb. So at any rate, that's just kind of convention. So then if you have anything above a binary relationship, so anything with a degree greater than 2, you use a diamond. And the diamond is labeled with the name of the relationship. It has an edge, an undirected edge to each entity involved in that relationship. So that's important with the diamond relationships. They are undirected edges. And in this case, here's one where we have a staff member registers a client at a branch. And here's one where a guest books a room at a hotel. And someone asked the previous lecture whether the fact that it's a diamond with just 4 obvious connection points, whether it's possible to have relationships with degree greater than 4, and the answer is yes, but that I've actually never seen such a relationship. But then I did hasten to add also that I'm in academia, so I don't get involved in these just enormous projects. So I'm sure that in the real world, you could get projects that are big enough where you would end up with a degree greater than 4. Okay, now this is the wrong way to show such a relationship. It's 3 binary relationships. It's certainly true that a guest makes a booking in a hotel is involved in a booking and a room is involved in a booking. But when you draw it the way I have it here, it totally obscures the fact that there's actually a three-way relationship among those three entities. Here, it looks like booking is an entity, which it isn't. It's a relationship. So you got to be careful, especially beginners are kind of, it's hard to think beyond binary relationships, but you got to try to get in the habit of doing that. And I'm going to show you a trick a little later that might help you in deciding whether something's a binary relationship or a greater, has greater degree relationship. Okay, so then we moved on to recursive relationships, and those are relationships that point back to themselves. So an example would be where staff supervises other staff. And in this case, you often label the edges with the roles so that someone looking at a recursive relationship, it's often not as clear, even with the verb, it may not be as clear. Although here, I certainly think it would be clear without the role names. So I'm not going to, again, be too concerned if you don't put role names down for recursive relationships. It just sometimes makes them a little easier to understand. And then you also sometimes have two relationships between entities going in opposite directions, like you see here. And you actually don't represent that as a single double arrow edge, but a separate, two separate directed edges. So here we have staff manages a branch has or employs staff. And again, sometimes you, in these cases where it's kind of like a two-way relationship going, there's two relationships. It's not a two-way relationship. There's two separate independent relationships going in opposite directions between the two entities. Again, sometimes you might label the roles of the two entities in this relationship. But again, I think if you pick a good verb, you normally don't have to do that. And again, I'm not going to be picky about this on either homework or exam. You don't want to get your ER diagrams too cluttered either. So you have to weigh the cost of cluttering your ER diagrams against whether providing role names actually really provides additional clarity or not. Okay, so the third thing then is attributes. And they can be a property of either an entity or a relationship. For example, with booking, that's a relationship, but you still have attributes like date from and date to that are attributes of that relationship. And again, if a relationship has attributes, invariably it has to be stored as a relation, a separate relation. So we have three types of attributes. We have descriptive attributes, which provide descriptive information about the entity. We have identifying attributes, which are essentially keys. They uniquely identify an entity. And then we have foreign key attributes that provide a link to another entity. And you see that here I have labeled descriptive attributes as unstable and the identifying attributes as stable. The reason is that identifying attributes rarely change. Like your social security number is fixed in cement effectively. It will never change. Your student ID will probably never change. Whereas descriptive attributes are unstable. They could easily change. Like in the booking relationship, a guest could easily call us and say, we need to change the dates of our reservation. So I say they're unstable, whereas both identifying attributes and foreign keys tend to be stable. They rarely change. So then we have attributes, and you can have a simple or composite attribute. A simple attribute is a component with an independent existence. So it could be age, it could be, I'll also call it a date, as but some people would say a date is a composite attribute because it has a month, a date, and a year. I'm not going to get picky about that kind of stuff. I don't plan to test you on that kind of thing, but address might be considered a composite attribute consisting of things like a street, a city, a zip code. Those would have a state, those would have independent existence and be considered a composite attribute. Then you can also have single valued and multi-valued attributes, and single value for the attribute, multi-values for the attributes. And multi-valued attributes are a problem when you map them into the relational model because a cell can't hold multiple values, but we don't worry about that in an ER diagram. Instead, we simply have some notation for that, which you'll see in a moment. And multi-valued attributes are typically represented in a separate relation. So for example, actually I can show you that right now. So if you had something like, say, a phone number, you might have a branch. And a branch might have a phone number and it's multi-valued. So what you might actually do is you might have something like a telephone relation. And it would consist of branch number and phone number. And now each tuple is unique and each cell is single valued. And you could have multiple tuples for the same branch now. So you might have branch B03, phone number is 865-181-2300. And you might have another tuple, 865-418, like that. So multi-valued attributes typically handled by moving them off to a separate relation. Sometimes what you'll do is if you know it's a upper bound on it, like 3, you could just have, like in the branch relation, you might say phone number 1, phone number 2, phone number 3. But the problem with that is it makes it really hard to query, because now you're writing all kinds of OR statements saying, get me all phone numbers. To get all phone numbers, you have to say, select phone number 1, comma, phone number 2, comma, phone number 3. Or if you're looking for a phone number, you have to say, select branch number from branch where phone number 1 equals this, or phone number 2 equals this, or phone number 3 equals that. And that gets to be pretty verbose and unmanageable. So even when a multi-valued attribute has a fixed number or fixed upper bound on the number of values, you typically still move it off to a separate relation. It just makes things a lot easier to deal with. Okay, and then you have derived attributes, which are attributes that are derivable from a value of a related attribute or set of attributes. And they are not explicitly represented in a database. That is, they're not physically stored in the database, but you may see them in the ER diagram because they're useful attributes that we want to be able to deal with. They typically show up in views. So there's 3 types of derived attributes. Most common would be attributes computed from an aggregate function like your total staff count. or total rooms occupied at some hotel. You, in the homework assignments, though, have seen examples of the other two types. So you might compute an attribute from two columns in the same relation. So for booking, you might want duration of guest stay, but you would not want to store that explicitly in the relation because it's actually redundant information. You can compute it from the date to and date from fields. And if at all possible, we omit redundant information from a database because it makes it easier to get inconsistencies, because if we do updates, we have to make sure we update every piece of redundant information. So in this case, rather than physically storing the duration of the guest stay, we could simply calculate it. And then the third type of attribute is computable from columns that belong to different relations. So could go even further and say that the cost of a guest stay is the product of the number of days in the booking, which you compute from the booking relation and itself is a derived attribute, and then you multiply it by the room cost from a room. So again, three types of attributes. You have composite, multi-valued, and derived. Okay, and let's just actually show that in a ER diagram. So normally if a attribute is the primary key, you label it as PK, the abbreviation to indicate that it is part of the primary key. If you have a derived relationship, so down here, total staff is a derived attribute. It has a slash in front of it. Composite relationships are shown with indentation. So here is the name of the composite attribute, and here are its sub attributes, or it's the attributes that compose it. So they're showed as a indented. And in the relation itself, you would probably store street, city, and postcode rather than address. So only in the ER diagram would you see address. So typically when you map it into a physical relation, the composite attribute would actually be stored as its individual components. So composite attributes tend to be this conceptual notion that you represent in an ER diagram, but when you again move to physical storage, you typically store the composite attribute as its separate sub attributes. And then if you have a multi-valued attribute, you typically show both the minimum and the maximum number of values that you could possibly have. If it's infinite, you use a star. So if you want it to say that there was an arbitrary number of telephone numbers, then you could say 1 ... asterisk, and that would indicate an infinite number. Okay, so derived attributes, a slash in front of them, composite attributes indented, multi-valued attributes have the number of both the minimum and maximum number of attributes in brackets, and then you typically identify any attribute in the any attribute is going to be identified with PK. And I'm going to have to try to get my mouse back. No, there we go. Okay. I have my mouse. else. There we go. Okay, so we've already talked about keys, so I'm not really going to worry too much about keys since we've already talked a lot about them. Composite key is simply a candidate key that consists of 2 or more attributes. So if you ever hear the word composite key, it's just a candidate key that's 2 or more attributes. Okay. Any questions thus far? Because I know this was actually kind of a lengthy review before we move on to the new stuff. No questions? Okay. So with entity types, sometimes we talk about a strong entity type versus a weak entity type. So a weak entity type is one that, is dependent, its existence depends on some other entity type. So it still has some kind of physical existence, but if you eliminate it, the strong entity type, then it would disappear. So good example in the hotel relation. Hotel is a strong entity type. Room is a weak entity type because the existence of rooms is dependent on the hotel. If the hotel disappears, then the rooms associated with that hotel also disappear. So room would be a weak entity type. Okay, another example, a project and its tasks. So a project may have 1 or more tasks associated, or 0 or more tasks associated with it. And the task in this case, it has a physical thing. It's a name, a description, some amount of time to finish it, might have some prerequisite tasks, but it's a weak entity because if the project disappears, the tasks disappear as well. So you sometimes hear this discussion of strong and weak entity. There we go. Then you also sometimes talk about supertype and subtype entities, and this is just like having superclasses and subclasses in object-oriented programming. So a supertype entity is just provides a convenient grouping construct for multiple related sub-entities. So for example, at a university, we might have, say, person as the generic entity, and then as subtype entities, we might have professor, student, staff as subtype entities. Now, we might also represent that simply as a attribute, and just have person as the single entity, but sometimes it helps to actually have subtype entities specifically stored as relations in the database. For example, student, staff, and employee all have very different attributes associated with them. Like professor and employee have salaries. I'm sorry, professor and administrator have salaries, but student may not. Student may have some other things associated with them, certainly courses that they're taking, their GPA is an example, maybe some financial aid information that the other entities don't have. So you actually want to store each of these entities separately. So in this case, you would group common attributes with the supertype entity. So the person might have a name, an address, an ID associated with them, but then you would elaborate additional attributes in each of the subtype entities. And the way you show that in an ER diagram, it can get a little bit cumbersome, but you start with an enclosing rectangle, which I have here, person, and the common attributes to all persons, which is ID, name, and email. And then within that rectangle, you have subrectangles representing each of the subtypes. So here's student, faculty, administrator, and actually could have probably had another one for staff. And you can see here, each of them is elaborating additional attributes that are kind of unique to that subtype entity. Okay, so again, there'd probably be for this entity diagram right here would probably be mapped to 4 relations in the database: a person relation, a student relation, a faculty relation, and administrator relation. And then the 3 subtypes would have a foreign key pointing back to their supertype objects. So they're actually, for each student, faculty, or administrator, there would be a person object. So you actually do need to, in each of them, you would map back to, so if you had, for example, faculty, it probably would contain the ID as a foreign key. This would be a foreign key that would map it back to its entry in the person relation. So each faculty member would have a tuple in both the person relation and in the faculty relation. Each student would have a tuple in the person relation and in the student relation. And then each student also would contain a ID as a foreign key pointing back to the super type. And for those of you doing the database project, the graduate students doing the database project in a couple weeks, you'll find that one of your types will be best modeled as a supertype subtype relationship. So this will come into play for the graduate students. Probably will not come into play for the undergraduate students, certainly not in the homework assignments. Okay, so then here's an example where a relationship can actually have attributes. So we have a newspaper advertises property for rent. So this is a binary relationship, but it actually has 2 attributes: the date for the advertisement and the cost of the advertisement. So the way you normally show that is with a separate separate box, but it's not labeled. So here you labeled the entities. Here there's a box, but you only have the attributes, and the where you would have a label for the entity, it's blank, but then you have a dotted line leading down, and that indicates it's a set of attributes associated with this relationship. Okay, so we've now covered entities, relationships, and attributes, and we're going to move on to some other things identified with relationships. They're called structural constraints, and what we're going to be concerned about is what is called multiplicity. So just like a multi-valued attribute can have 1 or more attributes, in a relationship between 2 entities, you can have 1 or more, or actually 0 or more instances of the entity involved in that relationship. So for example, you will have one branch can have, say, 1 to many employees associated with it. Or if a branch could have, is being under construction and does not yet even have employees, it would be 0 to many instances. Whereas a staff member belongs to exactly 1 branch, a minimum 1, a maximum of 1. So when we're talking about multiplicity, we talk about the upper bound and the lower bound on the number of instances of participation we can have in that relationship. So cardinality is the upper bound, participation is the lower bound. So with multi-valued attributes, the phone number I showed you earlier, the participation rate was 1, the cardinality was 3. So here's the formal definition. Cardinality, maximum number of possible occurrences of that entity in a relationship. Participation, the minimum number of entities in that relationship. So for example, if I have 0.1, it means a minimum of 0 and a maximum of 1 entity may occur in the relationship. So here is an example of how you show it in an ER diagram. You have the cardinality, I'm sorry, the multiplicity is on each side of the edge, and here a staff may manage 0 or 1 branch. So a staff may manage a minimum of 0 and a maximum of 1 branch. A branch is managed by a minimum of 1 staff member and a maximum of 1 staff member. Okay, so there's, we'll show you some other relationships. Actually, let's go and look at a couple other relationships. So here is what's called a one-to-many relationship. So a staff may oversee 0 to many properties, whereas a property may be managed by a minimum of 0 staff and a maximum of 1. And when you're coming up with these ER diagrams, you have to talk to people and figure out often whether it's 0 or 1, because that's important. We'll see later that 0 can create connection traps. So oftentimes we really would prefer that it be 1.1 for our convenience, but if it really is 0, that's how we have to model it. And then we just have to come up with ways around it if it creates issues. You can see here the asterisk used to denote an arbitrary number. So when you are putting these numbers here, it again shows for that entity how many occurrences there can be for each thing on the other side. So for each staff member, 1 staff member can manage 0 to many property for rent. So when trying to come up with multiplicity in a binary relationship, assume 1 on this side and then decide how many, the fewest possible and the most possible, and put that number over here. Okay, here's an example of what's called a many-to-many relationship. So a newspaper can advertise 1 or more properties. So we'd probably say if it's not advertising a property, perhaps it should not be in our database. Although you could argue maybe it's just not right now advertising any properties. So again, that's where you get into, is it 0 to many or is it 1 to many? Something you have to talk about with the person for whom you're designing the database. And then on the other side, we have for 1 property, that may be advertised by 0 or more newspapers. So if the property is leased, clearly we should not be advertising it unless the lease is expiring. But if the property is leased, we're probably not advertising it. If it is available for lease, we might be advertising it in multiple newspapers. So here it's 0 star for number of newspapers associated or that may advertise 1 property. and then one newspaper may advertise one to many properties. So coming back here, we'll also talk about the degree of a relationship. So multiplicity refers to both sides of the relationship, whereas degree refers to the maximum cardinality. So if the maximum cardinality on each side of the relationship is 1, we call it 1-to-1. If on one side there's many, on the other side it's 1 to many. And if it's unlimited on both sides, it's many to many. So I had an example here of each. Here, staff manages branches a 1-to-1 relationship, meaning one staff can manage exactly one branch. Here it is 1 to many. A staff can oversee 0 to many properties. And I can tell you this is the easiest one for directed edges. That should always go from the 1 to the many. The other ones where it's 1-to-1, you have to choose, and many to many, you have to choose. But when it's 1 to many, directed edge should always go toward the many. Okay, because the foreign key is always going to be with the many. It's never going to be with the 1. And here's the many to many relationship because the cardinality is an asterisk in both of them. Okay. So again,
Dr. VC?
yes, go ahead.
I'm sorry. For the star for the many to many, what did you say about the directed edge? I'm sorry.
Oh, for many, you're just going to have to choose whichever one sounds best to you.
Oh, okay.
It's just, so here newspaper advertises property for rent seems to work better than property for rent is advertised by newspaper. Remember, I prefer action verbs. So is a passive verb. So it just seemed better in this case for me when I thought about it. The way I got the action verb was with newspaper advertises properties for rent. So I made it point to property for rent.
Okay.
But, you know, let's say that you think of a property for rent as appearing in a newspaper, then you might decide to direct it the other way, and that's fine. So many to many can easily go either way. Okay. Now 1-to-1, remember that one, there's going to be a foreign key involved. And in that case, the edge should be directed toward the entity that contains the foreign key. So for 1-to-1 and 1 to many, it's pretty cut and dried, in my opinion, how the edge should be directed. It's in the 1-to-1 case, it's to the entity containing the foreign key. In the 1 to many case, you definitely direct it toward the many. It's only in the many to many case you have a choice, and it's kind of how in your head you see it, how you can compose an action verb. Okay, so with a relationship, it's typically a noun verb noun relationship. The entities are the noun, the relationship is the verb. Okay. So again, just another trap you'd want to avoid is that with a binary relationship, it's easy to think of the advertisement because it's a relation. You think, oh, every relation is an entity, but that's not true. So an advertisement is not an entity. It is a relationship between a newspaper and a property for rent. So what you see here is the wrong way to show that relationship. It looks here like advertisement is an entity, and you're listing 1 to many advertisements in the newspaper. And then as you see, the property for rent appears in 0 to many advertisements. And that is not the right way to write or draw it, simply because it obscures the fact that advertisement is not an entity. It's a relationship between newspaper and property for rent. Okay. Now, multiplicity gets more complicated when you have complex relationships whose degree is greater than 2. And you're going to have to come up with a multiplicity for each entity in the relationship. And I find that it's often easiest to try to think of it as a function. So if you have a relationship D, so think of this as the booking relationship among 3 entities. So if you want it more concrete than A, B, and C, think of it as a booking relationship. A, B, and C are hotel, room, and guest. So when you're trying to come up with the multiplicity for one of the entities, pretend that you have one instance of each of the other 2 entities, and then figure out what the multiplicity should be for the remaining entity. So here, if this is booking, A is hotel, and B is room, that means that we're asking how many guests can have a booking with a certain hotel and room. And at any time in the booking relationship, we could have multiple bookings on different dates. So it would be 0 to many in that case. If it was a room and a guest, so now a specific room and a specific guest, and now we're asking how many hotels could be associated with that room and that guest. It could be many, because that guest could be booked into that room on multiple different dates, or booked in. Okay, looks like I'm back. I think I lost y'all for a moment. Yep, sorry about that. So I'm back, as they say. Arnold Schwarzenegger, I'm back. So sorry about that. Can everyone hear me again? Raise your hands. Can you hear me?
Yep, we can hear you.
Okay, I need to share my screen again. Okay, can everyone see my screen? Very good. Okay, good. Okay. Okay, so as I was saying, when I lost the connection, I think I was working with a relationship between a saying that I have a booking, trying to figure out the participant or multiplicity rate for a hotel. So I'm assuming that I have a room and a particular guest. Question is, how many hotels could there be for that room and that guest? And it turns out the guest might not be staying in that room at all, so it could be 0. And depending on it, the guest could have a booking at the same room in different hotels. So it turns out that it's actually 0 to many, because you could have, if you think of it that way. Now, if you think of it as for a single booking, can you only have how many hotels can be associated with that booking? Then it is 0 to 1. So I probably would actually, this is where it definitely gets, you have to have experience. And I know it's not easy, but I would actually tend to say that, believe it or not, this is a 1-to-1 relationship, because what I'm really saying is I have a booking, and in that case, the guest has to stay in exactly one hotel for that booking. Can't be many hotels. So I would tend to say that was 1-to-1. And then if I had booking guest and hotel, well, I can have guests at more than one hotel. So I can, right now, I might have a guest that doesn't have any bookings, or it could be that guest right now may be booked at multiple hotels. Okay, so that's kind of how you want to think about it, is a function, and given a guest and a hotel, how many, I'm sorry, rooms. This is rooms, not bookings. So I'm actually coming up how many rooms. And in fact, I have to change that because really for a guest is only supposed to be staying at exactly one room at a hotel. Now, again, you could say, well, if they have multiple bookings, then it could be one to many, because they could have many, they could have several bookings at the same hotel. I would probably write one to one here, because for a booking, they can only have be staying in one room for that booking. We don't have double booked. A guest can't be double booked in multiple rooms. If I allowed a guest to double book multiple rooms, then it would become one to many. So this would indicate that I allowed double booking. By a guest, which I don't want. So here's kind of an example of a business constraint. I don't allow double bookings. So I would say it has to be one to one, that a guest can be in exactly one room at a time. Okay, so you have to kind of think about what are the implications. If I say one to many, that's the implication, is that I'm allowing a guest to double book rooms on the same date. And again, this takes time. It took me, if you look at my homework solutions over the years, you see that my homework solutions changed as I got more sophisticated with it. I kind of moved into dealing with databases a lot about 7 or 8 years ago. So as I got more experience, my homework solutions changed as I myself got better at computing multiplicity. So I'm not going to claim this is easy. Computing them for multi-degree relationships is not an easy thing to do. So this was another example. Staff registers a client at a branch. So we say that a staff member at some branch may register 0 or many clients. In fact, we would like them to register 0 or many clients, but that a client is registered at exactly one branch by a staff member, and a staff member registers a client at exactly one branch. So a client won't be registered at 2 branches or 3 branches. A client will be registered by a staff at exactly one branch. So notice again, no directed arrows in this case, all undirected, but each entity still has a participation or multiplicity associated with it. Okay, before I get to problems with ER models, just want to talk briefly. Yep, I have a little bit. So you can kind of go back and forth between ER diagrams and relations. So if you have a relation, like you've come up with a relation and you have booking, and you see that it has hotel number, and it has a room number, and it has a guest number, and then some other attributes, there's a good chance that this is a relationship. It's not guaranteed, but relationships, relations have at least 2 foreign keys. So oftentimes an entity may have 1 foreign key, but it won't have multiple foreign keys. So anytime you see a relation that has multiple foreign keys, you got to get your antenna up that this might be a relationship. It might not be. It's certainly possible that a entity could have 2 foreign keys and not be a relationship. For example, I could have staff, and it has a branch number for where the staff member works, and it has another one for manager, and these are both foreign keys, this being a staff number. And in this case, staff is not a relationship. It is a entity, yet it has 2 foreign keys. So my rule doesn't always hold, but you just need to be on the alert for when there's multiple foreign keys in that relationship, in that relation, then it should raise your attention to the fact that it may be a relationship. And I guess to go further, if it seems like you can compose some kind of sentence that involves all the foreign keys, then it's a relationship. So typically, if it's a relationship, then all the foreign keys will be related. Using a sentence. So for example, booking, a guest books a room at a hotel. You can't do that with a staff relation. That's different. A staff works at a branch. A staff is managed by a manager. So it's 2 separate sentences. So I know that's not perfect, but when you're designing ER diagrams, you'll also often, it's almost like you have 2 pieces of paper. On one piece of paper, you have the diagram. On the other piece of paper, you have the relations thus far that are kind of implied by your diagram. And so you can kind of go back and forth between the 2 to help you figure out which are entities, which are relationships. And then remember, you can also have multi-valued attributes in a relation. So you do have to realize that when you have a relation, it can be one of 3 things. It can be an entity, it can be a relationship, or it could be a multi-valued attribute. So you have to be alert to each of those, that it also could be a multi-valued attribute, like phone number that I showed you was a multi-valued attribute. Okay, so questions about that? Okay, so last thing to cover is the problems that can arise with ER models. And they're connection traps where essentially you lose information. And the 2 main types of traps are fan traps and chasm traps. So here's an example of a fan trap. So we assume that an organization has a number of divisions. Each division operates its own set of branches, and each division has staff associated with it. So think of a bank that has bought several other banks. So let's say we have Bank of America, maybe it owns First Horizon, and it owns People's Bank, and it owns Mountain Bank. So it calls each of those a division. So First Horizon is a division, Mountain Bank is a division, People's Bank is a division. So we think of each bank as having staff, but also each bank as operating some number of branches. Okay, and each of these you can see is from the division. A division operates one-to-many branches. A division has one-to-many staff. So this is what's called a semantic net diagram. Don't worry, I'm not going to make you draw them, but it kind of shows what is going on. So we have staff SG37 is employed by Division 1, and we have staff A9 is employed by Division 1, staff 21 employed by Division 2, Division 1 operating 2 branches, Division 2 operates 1 branch. So a common query is, at which branch office does staff number SG37 work? And the answer is, we don't know, because there's this connection trap right here where you can see everything gets pinched to a choke point, and then it comes out again. And the problem is the staff member may be employed at either branch B3 or branch B7. So a fan trap causes this pinch point that loses information. In this case, we can't figure out which branch employs that staff member. So the solution is typically to reorient the diagrams or reorder the entities. So before I had division in the middle, but it's actually, if we understand the relationship better, we realize that actually a division operates branches, and then staff are associated with branches. So we just reorder them, and we can still answer the question of which staff is employed by a division by finding out which division operates the branch. So by reordering the entities, we haven't lost information, we've just gained information. So now you can see this same semantic net, but now it's easy to find out which division or branch SG37 works at, because there's no pinch point until you get back to the division level. So fan traps, they typically occur when you have multiple one-to-many relationships leaving an entity, and at least one of the one-to-many relationships is a transitive relationship. So basically, the issue is that you put in the original diagram, you put division in the middle of that transitive relationship rather than putting it at one end of that transitive relationship. And so there, fan traps, again, the big thing is they arise when you have two or more one-to-many relationships leaving the entity, and those two relationships can be formulated as a transitive relationship. So you have to then just make sure you got the order correct. Okay, the second type of problem is a chasm trap. And a chasm trap appears or occurs when it looks like there's an unbroken path between two entities, but somewhere on the path there's a zero participation rate that disrupts it. So here's an example where we have a branch has or employs some staff, staff oversee properties, and so we think that we can determine which branch oversees each property, because we see we can get from a branch to a staff and from a staff to a property for rent. So we should be able to determine for each property which branch it's associated with. But the problem is right here. Right here, you have this big 0 for staff. Okay, so I'll even circle it because it's so important. Okay, right there, that can cause there to be no staff, and therefore it breaks the path. Okay, and again, we can kind of show it as a semantic net. I can get control back. Okay. So here's the semantic net, and you see the problem. So property PA14 isn't associated with any staff, and therefore we can't find out which branch manages it. So there's a broken path because of the fact that staff has a 0 participation rate in its relationship with property for rent. There's no good solution. FanTrap has a good solution. You reorder the entities for a FanTrap. A chasm trap, you can only solve it, well, you can solve it in one of two ways. The first way is to add an additional relationship. So here we add an additional relationship, branch offers property for rent, which means we add an additional key to property for rent, which is a branch number. So now we can answer our question for P14. We see that it belongs to branch B7. So we can now find which branch is associated with any given property. But the problem is we've also introduced redundant information into the database for the times when there is a staff associated with a property for rent. So let's say that staff SG37 moves to branch B7. We have to not only update the fact that SG37 has moved to branch B7, but we also now have to remember to update this offers relationship. So we're going to have to change also a foreign key in property for rent to make sure that it points to B7. So the problem with solving a chasm trap by introducing additional relationship is it introduces an additional foreign key, which is in many cases redundant. It's only necessary in the case where there's a missing staff member. And in all other cases, it's redundant, and we have to remember to update two pieces of information when a staff moves to a new branch. The other thing we can do is convince the person for whom we're designing the database to change the relationship so that it becomes one-to-one. So we could say, okay, if we have not yet assigned a property to some staff member, maybe we just assign it to a default individual, such as the branch manager. And then that changes the participation rate here from 0-1 to 1-1, and then it becomes an unbroken path. So the other solution to a chasm trap, which is often more desirable, is to say, okay, can we associate a default value in the case where the participation rate would be 0? And if we can associate a default value, then we change the participation rate to a 1, and it breaks the chasm trap too. Okay, so here's a summary. Chasm traps occur when the diagram suggests a transitive relationship exists, but the path may not exist because there is a 0 participation rate. So notice both fan traps and chasm traps have a transitive relationship. It's just there's a difference. In the case of the fan trap, the ordering of the relationships was wrong. In a chasm trap, there is a 0 participation rate on the path, and that breaks the path in some cases. And the ways we fix the trap, one, we add a direct relationship between the two entities that are disconnected by the trap, but that solution adds redundant data, or we convince our customer / client to allow a default value so that the participation rate can be changed to 1. And the second solution is preferable, but if our client is insistent that there is no default value and they want to allow a null value to be there, our only way to address it is to introduce a new relationship, which means a new foreign key and a bit of redundancy. Okay, so with that, we are done for today. What is up next time is actually a pretty important lecture for the homework assignment. So next time I go over this investment firm case, and I suggest you just scan it. It's a previous test problem. And what I find is if I don't spend an entire class period going over a comprehensive case, then both the homework assignments and the test end up being really bad. So it really helps for me to walk through an example to try to show you how to derive a ER diagram from essentially a word problem. So that's what we'll be going over next time. So with that, I'm going to let you all go, but if you have questions, feel free to stay and ask, and I will see you on Thursday.